Welcome to this explainer. Today, we're diving into something completely invisible, yet so ridiculously powerful that it literally powers the stars in our night sky and fundamentally shapes the physical world around us. We are, of course, talking about nuclear chemistry. Now, this isn't your standard high school science class where we're just mixing a few colorful liquids in a beaker. No, we're going to journey deep into the absolute core of reality, exploring the incredible massive energy locked away inside the tiniest building blocks of existence.
Here is our roadmap for today's explainer. We'll kick things off inside the atomic nucleus before moving into understanding radiation and decay. Next up, we'll look at unleashing massive nuclear energy, followed by real-world applications. And finally, we'll wrap up with radiation hazards and safety.
All right, part one, inside the atomic nucleus, the microscopic foundation. To really get this, we need to shrink our perspective down to the absolute smallest scale imaginable.
So, what exactly is nuclear chemistry? Well, it's the branch of science studying the structure, stability, and transformations of atomic nuclei. Think about ordinary chemistry for a second. Standard chemistry is really just about shuffling electrons around the outside of an atom, kind of like a cosmic dance of trading and sharing. But nuclear chemistry? It completely ignores that outer shell. It fundamentally alters the core identity of the atom itself.
You know, there is a very clear division of labor within the atom. The electrons orbiting the outside carry a negative charge, and they're the stars of standard chemistry. But the true heavyweights? Those are the protons and neutrons packed super tightly together in the center. Even though this nucleus is unimaginably tiny, it holds practically all the mass of the atom. It is the absolute anchor. The protons have a positive charge, the neutrons have no charge, and together they dictate exactly what element we are looking at.
So how do we measure this core? It's all about the numbers. The atomic number is simply your number of protons, which determines the element. The mass number combines those protons and neutrons. This brings us right to isotopes, because you can have the exact same element, like carbon, but with a different number of neutrons, giving us variants like carbon-12 or carbon-14. Now here's the really important part. Every atom desperately wants to be stable. This requires a balanced ratio of neutrons to protons. Light elements usually want a neat 1-to-1 ratio, while heavier elements need more neutrons. When that ratio is thrown off, the nucleus becomes unstable, and well, the atom gets restless.
Which brings us smoothly to part two, understanding radiation and decay. Let's look at exactly what happens inside that unstable nucleus.
When that atomic balance is off, the nucleus spontaneously emits radiation to try and find some stability. There are three main types here, and they definitely escalate in power. First is alpha radiation. Think of this as a heavy, bulky chunk of a helium nucleus, just 2 protons and 2 neutrons. Because it's so physically large, it has really low penetration power, but it causes a ton of ionization. Step it up a notch to beta radiation, and you have an electron or positron being fired out at super high speed. It's smaller, it's faster, and it has medium penetration. And finally, gamma radiation. Now, these aren't physical particles at all. They are pure high-energy electromagnetic waves. As you might guess, they have very high penetration power, blasting right through most normal materials.
Now, don't let this half-life formula intimidate you. What you need to take away from this isn't the complex algebra, but the core concept itself. The half-life is simply the time it takes for exactly half of a radioactive substance to decay. The crucial insight here is that decay is an exponential drop, not a linear one. It halves, then it halves again, then it halves again. It curves downwards, getting slower and slower as time goes on, but it never quite instantly disappears.
So far, we've only talked about spontaneous, natural decay, but there's also something called artificial radioactivity. Radioactivity isn't just something that passively happens out in nature. Humans can actually induce it. By deliberately bombarding perfectly stable atoms with subatomic particles, we can force them to become unstable. For example, if we hit stable aluminum with a neutron, we can artificially transform it into radioactive phosphorus. This is an absolute game changer, giving us the ability to custom-make radioactive isotopes for crucial research, industry, and even medical treatments.
All right, part 3, unleashing massive nuclear energy. We're transitioning now from gradual microscopic decay to the sudden explosive release of massive energy.
Let's see how this all builds into real-world power generation through two completely opposite reactions. In nuclear fission, a massive, heavy nucleus, like uranium-235, is literally split apart into smaller nuclei. That splitting releases a huge burst of energy, and it's exactly the process we use right here on Earth in our nuclear reactors. Conversely, nuclear fusion takes incredibly light nuclei, like hydrogen, and smashes them together to form a heavier nucleus, like helium. This is the exact reaction that occurs in the stars. Now, fusion releases vastly more energy than fission, but as of right now, it is immensely difficult for us to control here on Earth. And the secret behind all this unimaginable energy? It's E equals mc squared, easily the most famous equation in history. In nuclear chemistry, there's a wild phenomenon called the mass defect. See, when nuclei split or fuse, a tiny fraction of their physical mass literally vanishes. Poof! But it doesn't just disappear from reality. It transforms entirely. That vanished mass, which is the m in our equation, is multiplied by the speed of light squared. Because the speed of light is such a massively huge number, even a microscopic speck of vanishing mass translates into an utterly raw, massive explosion of pure energy.
Moving into Part 4, Real-World Applications and Uses. We know the power is staggering, but how do we actually harness it? Let's zoom out to the macroscopic scale for a minute.
Nuclear chemistry reaches into surprisingly diverse areas of our daily lives. In medicine, it's out there saving lives right now. We use radiotherapy to target and treat cancer, and we use radioactive tracers for highly detailed PET scan imaging. And energy, as we just mentioned, nuclear power plants generate massive amounts of our electricity. But its reach even extends to agriculture. We use radiation to induce beneficial mutations to improve crop yields and even to sterilize insects for pest control. And in industry, radioactive isotopes are constantly used to measure the precise thickness of manufactured materials or to detect hidden leaks in massive pipe networks. So, let's look objectively at how this stacks up for our power grid. When you compare it to fossil fuels, nuclear energy boasts a vastly higher energy output and produces very, very low atmospheric CO2. The big trade-off, however, is in the waste. While fossil fuels are pumping greenhouse gases straight into the air, nuclear energy produces radioactive waste that has to be incredibly carefully managed. Ultimately, nuclear is largely seen as a long-term sustainability option, whereas fossil fuels are intrinsically limited. Because of that radioactive waste, we smoothly transition into our final section, Part 5, Radiation Hazards and Safety, and exactly how we manage those risks. We really must be impartial and address the very real biological hazards associated with this field. Radiation is an invisible force that absolutely must be respected because it actively damages living tissues. When those high-energy particles or waves hit our cells, they can cause actual cell mutation. Over time, or with high enough exposure, this can lead to cancer, and if it affects reproductive cells, it results in severe genetic damage. Make no mistake, this is the very real dark side of having access to that immense power. So, with all that in mind, how do scientists and medical professionals stay safe while working with this every single day? They follow 3 highly actionable safety steps. Step 1. Use heavy shielding. Materials like thick lead or dense concrete are absolutely required to block high-penetration rays like gamma. Step 2. Strictly limit your exposure time. The less time you spend near a radioactive source, the lower your total dose is going to be. And Step 3. Maintain a safe distance. Radiation intensity drops off dramatically the further away you step from the source. It all comes down to shielding, time, and distance.
Okay, let's bring all of this together. We've covered a ton of ground today. We saw that nuclear chemistry deals exclusively with changes right at the nucleus level, far, far deeper than normal chemistry. We learned that radioactivity is actually a natural, spontaneous process of unstable atoms desperately seeking balance. We saw that the immense energy released perfectly follows Einstein's E equals mc squared. Whether it's splitting atoms in a reactor or fusing them in the stars, the raw power is just undeniable. And finally, we saw that our mastery of this science has given us life-changing applications, ranging from cancer treatments to powering our biggest cities.
And that brings us to the end of our explainer. I have to ask you, will you look at the stars and the world around you just a little bit differently tonight, knowing that they are entirely governed by the invisible, microscopic shifting of atomic cores? The tiniest building blocks of our universe truly do hold its greatest secrets. Keep asking questions and keep seeking to understand them.